Welcome to Chapter 2. Chapter 2 concerns itself principally with atomic structure, the constituent parts of an atom that we'll be concerned with, the naming of compounds, how chemical reaction happens, atomic theory as it was first described by John Dalton, atoms, ions, a whole ream of different ideas that we're going to pass through fairly quickly. There's not a lot of math in this chapter. Some of you will like that, some of you won't. Let's go ahead and start with Democritus of Abdera. Now, Democritus was a pre-Socratic philosopher. He existed in the years between 460 BC, 370 BC, so that was a long time ago. And he was given credit as being one of the first people to describe matter as being composed of little tiny indivisible particles, which he called atoma. And that is, as you might guess, where we get the modern word atoms. And Democritus was a very interesting guy. He was known by some lights as the mad philosopher. Life without laughter is like a road without an end. I'm pretty sure Democritus had a very good time. Quotations by Democritus. I would rather discover one scientific fact than become king of Persia. Not really a power seeker. Cared about knowledge, about understanding nature and the world, how it worked. Everything existing in the universe is the fruit of chance and necessity. That couldn't have been a very popular view in his day, in a time that was dominated by gods, spirits, gens, all sorts of ethereal, imagined entities which ruled the world. Nothing is so easy as to deceive oneself for what we wish that we readily believe. All you have to do is go on the internet to know that that's true. People believe all kinds of screwy things. Nothing exists except atoms and empty space. Everything else is opinion. And oh my, aren't there a lot of opinions out there? We are concerned in this course with science. What the data indicates, not somebody's grand, beautiful, or not so beautiful idea of what the universe actually is. What can we demonstrate? So let's take a look at what we think we know. All right, first of all, John Dalton came up with atomic theory, and it was really a revolution in his day. He was an English chemist. He was an experimentalist. He was a meteorologist. He took over 200,000 meteorological readings in his day. Kind of a peculiar guy who enjoyed bowling. It was a lawn bowling, or a form of bowling in England at that day. But he came up with atomic theory that explained the law of conservation of mass, which had been initially discovered by Lavoisier. Now, he imagined that all matter was composed of tiny, indivisible particles, which were called atoms, from Democritus. And Dalton's theory was a model for the physical world and explained a great many things about experiments that had already been done. So let's take a look. So here we have Dalton's atomic theory, which said that each element is composed of extremely small, indivisible particles called atoms. This is mostly correct, but we can say that atoms are not indivisible. So this was actually incorrect, because now we know that atoms consist of protons, neutrons, electrons, and then you can take protons and neutrons and you can further subdivide them into quarks, and who knows how deep that particular rabbit hole goes. But he certainly didn't have the instrumentation to come to a conclusion other than that atoms were indivisible in his particular day. All right, all atoms of a given element are identical to one another in mass and other properties. All right, so we're going to split this postulate up into the first statement, which ends here, and the second statement. We'll get to that in a second. All atoms of a given element are identical to one another in mass. This turns out not to be precisely true, and that's because of the presence of isotopes. And isotopes are species that have the same number of protons. It's the same element, but they have different numbers of neutrons, and neutrons weigh just a tiny bit more than protons do, and so that will cause the mass of different isotopes to be different. So I can have carbon-12, which is most of the carbon that's on the planet, but I could also have carbon-14, which is a radioactive isotope of carbon that we use in radiocarbon dating. So that part of the statement was false. However, but the atoms of one element are different from the atoms of all other elements, and that's true. So an atom of, let's say, gold, and so here's gold, and its atomic number 79, it's Au, and then an atom of, let's say, carbon, and carbon has 6 protons in the nucleus. So these two atoms, gold and carbon, are very different from each other, and they are the smallest particle of those elements that we call gold and carbon, respectively. Atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in a chemical reaction. This is a description of what we know as the law of conservation of mass. So if I have 2 atoms of hydrogen and I combine it with 1 atom of oxygen, I will make 2 molecules of water. Now, this is an expression of the law of conservation of mass. It's a balanced chemical reaction, which is, in fact, an expression of the law of conservation of mass. And then finally, compounds are formed when atoms of more than one element combine. A given compound always has the same relative number and kind of atoms. So here we have hydrogen, 2 hydrogen molecules, 1 oxygen molecule. The oxygen molecule consists of 2 oxygen atoms. The hydrogen molecule consists of 2 hydrogen atoms, but there are 2 molecules. They combine to form the compound. Water is a compound, and water always consists of 2 hydrogen atoms and 1 oxygen atom. That is a fixed ratio of hydrogen to oxygen in that compound. So let's talk about one of John Dalton's postulates, principally the law of conservation of mass, which simply says atoms are neither created nor destroyed in a chemical reaction. So what that means is if I have cake mix over here, so I've got some cake mix, and all the atoms of my cake mix, the water, the H2O that I put in here, the sugar, or whatever is going into my cake, all those atoms in a closed system, that is, if I take efforts to completely enclose that mixture and I come out with nothing but cake on the other side, all my atoms will be there. There will be no destruction of the atoms of hydrogen, oxygen, and cake mix. So if I have, let's say, 1 pound of cake mix, I'll get 1 pound of cake, 1 lbs of cakes. Okay? All right. And if I were a little bit more chemically about it, I would say, okay, I'm going to take 2 moles or 2 units of hydrogen, 2 diatomic molecules of hydrogen, 1 diatomic molecule of oxygen gas, and I'm going to react them, and that's going to give me 2 moles of H2O. And I don't think we've talked about moles yet, but 2 molecules of H2O. I'm not sure we've talked about molecules yet, but we'll get to it. But at any rate, if I have, let's say, 100 grams, 100 grams total over here on the reactant side, then I'll have 100 grams total on the product side. Now, 10.5 grams of that 100 gram total was hydrogen. The rest of it is going to have to be oxygen. So this would just be 100 minus the 10.5 grams. Okay, those aren't real numbers, but I think you get the idea. So Dalton's law of conservation of mass says that atoms are neither created nor destroyed in a chemical reaction. And then we have this really goofy word from Germany, stoichiometry, which literally means the measurement of the elements. So I used just a while ago 2H2 plus 1 O2 makes 2 H2Os. This represents the stoichiometry. This is an understood 1 right here. This is all understanding that I have 2 times 2, that's 4 atoms of hydrogen. I've got 1 times 2, 2 atoms of oxygen. Here I have 2 times 2, that's 4 atoms of hydrogen, and 2 times, and this is understood to be a 1, 2 atoms of oxygen. So law of conservation of mass is reflected in the stoichiometry, the coefficients of the chemical components of your reaction. Literally means measurement of the elements. You'll want to remember the word. So in chemical reactions, we write them as reactants. On the left, this is convention. The arrow means that the chemical reaction is taking place, or it just says produces, reactants produce, and on the right we put products. And that's our convention. You're going to want to remember that. We could write it as A, reactant A plus reactant B makes product C or produces product C. Here's another way to look at it. Same reaction of hydrogen plus oxygen making water. Here I've got 4 hydrogen atoms. That's my 2 times H2, and then my 1 oxygen atom, which is O2. It's a diatomic molecule, and that's going to make my 2 molecules of water, H2O. All right, and I can see that right here. I can see this is a hydrogen, this is a hydrogen, this is a hydrogen, this is a hydrogen. That's an oxygen. Oh, that's kind of tough to see. Oxygen, 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 and here are my hydrogens. Okay, so you get the same number of each type of atom of elements here. All right, and that is the law of conservation of mass for a balanced chemical reaction. And a chemical equation is a recipe on the atomic level for creating new molecules from existing molecules or atoms. A balanced chemical equation is an expression of the law of conservation of mass. And then you have at the end, up here, up top, this is the conventional way of writing a balanced chemical reaction. All right? So the subatomic particles that we will look at in this course are protons, neutrons, and electrons. Now, protons and neutrons, these 2 particles we will find in the nucleus of an atom. So these guys are in the nucleus. And then the electron, which is much, much lighter, about 1,800 times lighter than either protons or neutrons, and it is surrounding the nucleus. So we'll have a nucleus, which will consist of protons and neutrons, and then way out here, far, far away from our tiny, tiny, heavy, dense nucleus, we'll have electrons in what we call the electron cloud. Okay, so that's our basic structure. So protons, neutrons, and electrons. So the electron, its discovery, or the charge to mass ratio of the electron, and essentially the electron itself, is credited to a scientist known as J.J. Thomson, and he's 1897. And what he did using a device called a Crookes tube, he applied a high voltage, created a stream of particles through a pinhole. He manipulated those particles with negative and positive voltages and magnets, and he was able to manipulate the electron. He knew that it was attracted to positive plates, it was repelled by negative voltage, and it would impact a fluorescent screen. And he was able to compute the charge to mass ratio of the electron, and he was given the Nobel Prize for that discovery. It's interesting that at dinner parties, when he was called upon to give toasts, as he often was, he'd say, "Here's to the electron. May it never be of use to anyone." Well, it turns out the electron is not of just any use. It is something that we use every day. We're using it right now, and it is the basis for so much of our technology. Millikan oil drop experiment used the charge to mass ratio from Thomson's discovery. It was a crude device, but Robert Millikan had a source of ionizing radiation. What he would do is he would take oil and he would use an atomizer, like a perfume sprayer, and he would squirt a cloud of oil droplets. Some of those oil droplets would fall through a pinhole in a positively charged plate, and then he would apply ionizing radiation, X-rays, through a radioactive source, and he would ionize the oil droplets, and then he would manipulate the voltage on the positive and negative plates until he got the oil droplet to suspend in the, through attraction and repulsion, suspend in between. And he would look through the side of his device, and I've seen pictures of the device. It was actually made out of wood, using a little viewing microscope. And by doing that experiment, thousands of iterations, he was able to use Thomson's charge to mass ratio. He was able to figure out what the mass of the electron was. So here is our atom circa turn of the century, 1900. It was called the plum pudding model. In some circles, it was called the raisin cookie model. And what it was a smear of positive charge with negatively charged electrons embedded in more or less fixed positions in the plum pudding or raisin cookie. So that was what was put forward, and it's just a positive sphere of matter with negative electrons embedded in it, circa 1900. All right, so this was a golden age of experimentation. A lot of people were starting to experiment with radioactivity. There was a scientist, I believe he was originally from New Zealand, wound up in England. Ernest Rutherford had a very powerful lab in England, and he used ionizing radiation, a radioactive source. And what he did was he made a stream of particles coming from that radioactive source by simply having a pinhole in some sort of a protective sheet, and then he would apply a charge, positive and a negative charge, to these electrical plates, and he was able to split a single beam up into 3 beams. And you had a high degree of deflection of that beam for one of those particle streams, and he called those beta rays. They were attracted to the positive charge, and so it was assumed these are negatively charged, and we called those beta rays. There was a stream of particles that did not seem to be affected by the electrical charges, and they came straight through. They were undeflected. He called those gamma rays. They turned out just to be high energy photons. And then there was another stream of particles that split off, which we called alpha rays or alpha particles, and they were attracted to the negatively charged plate, indicating that they were positive, and the low degree of deflection indicated that they were much, much heavier than the beta rays. The beta rays turned out to be high energy electrons. The gamma rays turned out to be high energy photons. The alpha rays turned out to be helium nuclei with a positive 2 charge. So these alpha rays are helium nuclei. That is, it's a helium atom that's been stripped of its electrons. So there are 2 positively charged protons and 2 neutrons in the nucleus. So it's a relatively heavy particle compared to high energy electrons, which are really, really light. And then the gamma rays are just photons. These are just high energy photons. And so these are big old bowling balls of particles relative to the others. So what Rutherford did with those heavy alpha particles with positive charge is he did an experiment that led to the discovery of the atomic nucleus. So if you remember, what we had at the turn of the century was the plum pudding model, and you had this smear of positive charge with negatively charged electrons just sort of embedded in it. Now, what he did was he shot those big old heavily charged alpha particles into a thin piece of gold foil. If the plum pudding model was correct, alpha particles with the positive charge would just go straight through the thin gold foil, and most of them did. However, every now and then you'd get a deflection. You'd get one that was deflected in this direction, or reflected in this direction, or this direction. Some of those alpha particles were deflected to such a great degree that the conclusion was inescapable that there was something really heavy, really dense, and positively charged inside the gold foil. Here was the hypothesis that was the result of this experiment. Down deep in the center of an atom was a positively charged nucleus that was very heavy, very dense, from which these heavily charged, remember, these are alpha particles. They have a positive 2 charge, and they are bouncing off of that nucleus, but only every once in a while. Most of the alpha particles are going straight through. This indicated that most of the atom was just empty space, but down deep in the center of the atom was a heavy, dense, positively charged nucleus. And that is a famous experiment, that the Rutherford gold foil experiment that led to the discovery of the atomic nucleus.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So you should certainly know the subatomic particles, protons, neutrons in the nucleus, electron in the electron cloud surrounding the nucleus, really like so much moving fluff. You should be familiar with the giants of the period, J.J. Thomson, the discovery of the charge to mass ratio of the electron, Robert Millikan and the oil drop experiment, which used Thomson's information, his charge to mass ratio, to discover the mass of the electron. You should be familiar with the plum pudding model from the turn of the century and the radioactivity experiments of Ernest Rutherford. You may be familiar with one of the people conducting those experiments. His name was Hans Geiger, and he, along with Marsden, conducted the gold foil experiments, which led to the discovery of the atomic nucleus. Heavy, dense, and positively charged, and incredibly small relative to the atom. So the atom itself is mostly empty space. That's the nuclear atom. That's Rutherford's atom. The comparison is made for the nucleus in terms of size. If you were to take a golf ball and put it at the 50-yard line in the center of the Astrodome and then go to the outside of the dome, that would be where the electrons are relative to the nucleus. The nucleus is 100,000 times smaller than the atom itself, leading us to the conclusion, the inescapable conclusion, that the atom is mostly empty space. Other subatomic particles, protons, discovered by Rutherford in 1919. Neutrons, much more difficult to discover. James Chadwick in 1932. Difficult because they do not have a charge. So, characteristics of subatomic particles. Protons at 1.673 times 10 to the minus 24 grams. Neutrons at a tiny bit heavier, about 2,000 times heavier. 1.675 times 10 to the minus 24 grams, and the electron many, many times lighter than both the proton and the neutron. It's really feathers compared to billiard balls in terms of mass. 9.109 times 10 to the minus 28. I think that's about 1,800 times less massive. Charge on the subatomic particles. Protons are positively charged with a Coulomb charge of 1.602 times 10 to the minus 19 coulombs. Neutrons, no charge, as indicated by their name, and electrons with exactly the same magnitude of charge in coulombs as the proton, but opposite in sign. This is our convention. We call the electrons negatively charged. We call the protons positively charged. So what we're going to do is we need a new unit of mass, because I don't know about you, but 10 to the minus 24 grams, 10 to the minus 28 grams, that's really not something I want to work with or keep track of. So we're going to come up with a new unit of mass called the atomic mass unit, or AMU. Charge, we're going to normalize to +1 for the proton and -1 for the electron, and we still have a neutral charge for the neutron. In atomic mass units, and I'm about to show you where this unit comes from, the proton is 1.0073 AMU, neutrons 1.0087 AMU, and we have 5.486 10 to the minus 4 AMU for the electron. When computing the mass of atoms, we ignore the mass of the electron because it does not make a significant contribution.